Welcome to Lecture 23B. This is extension to the Lecture 23A, where we're going to look at the Divergence Theorem, which is in 3D, basically another tooling example. Materials comes from reading Assignment 4, Section 4.1.1. And again, the objectives are to develop the skills for applying the Divergence Theorem to geometrical problems. The concepts, conventions, and visualization skills, again, closed surface encloses a volume, and the surface area or vector points outwards from the surface that's enclosing the volume. Again, the second slide, as usual, is just a summary of the slides to follow. I just, though, would like to sort of make a note of two things. The first is that the last two examples, that's questions 39 and 47, should be attempted as homework questions before watching this video. Only watch the video for these examples if you're having difficulty. The problems are quite involved, but they are a good introduction to ECE 221, which is next term. It's the course on electromagnetics, so it might be good for you to try it out first. Secondly, that question 39 from the textbook has been modified, and one of the questions has been omitted. This has more to do with the organization of the material. There are parts of the textbook where they introduce other topics first, and of course we're not at that stage, and therefore one of those questions would not be possible to do, so I just removed it. And so it's better to read the question here rather than trying to refer to it in the textbook. All right, so we're going to take question 29 from chapter 17.8, and we're going to use the divergence theorem to compute the net outward flux across the boundary of the given region D. And the vector field is given by x squared minus y squared z squared. And the domain, or D, is a region in the first octant between the planes z equals 4 minus x minus y and z equals 2 minus x minus y. And so just, you may want to come back to this picture frequently. And of course, here's the link where you can look at it and view it. You can sort of see that the back face is this triangular blue region. And that if you were to look at this as surfaces, you would see the upper surface is a continuous surface, but the lower surface basically is not continuous because it starts off on an angle and then it just becomes a portion of the XY plane. So we can see that this might be a problem when you're integrating. It cannot be done in terms of a single integral. These are going to be the sides. The side in this case would be the ZX plane, and the back side that you see here would be the ZY plane. So you can also look at this, as we'll show shortly. If you were interested just at the domain, then you could say the domain would be the difference between the domain that's seen if we're just to look at this plane, subtract away from the domain if we're only looking at the domain which is from this plane back to the origin. All right, that'd be an easier way to look at it, and we'll show that in fact that's the case. But keep this in mind, and you may want to refer back to it or open it up in another window if you wish. All right, so here basically is the problem statement. Compute the net flux from the boundary surface enclosing the region using the divergence theorem. All right, so the divergence theorem is here. This is the left-hand side, which is basically a flux over the closed surface. And on the right-hand side is the divergence of the vector field integrated over the volume enclosed by the surface. Now, if you were to do the calculation on the left-hand side, it'd be an extremely difficult problem because you would have to break this up into 6 individual surfaces because the surface is not a smooth continuous surface. So we're not going to do that, as I stated. We're going to do the right-hand side. So we're going to compute the divergence of the vector field, which is what I've done here. Right? It's just taking the derivative of the x component with respect to x plus the derivative of the y component with respect to y plus the derivative of the z component with respect to z. If you do that, you end up with this expression here. And so then the integration is over the domain. All right, so what I'm going to do is I'm just going to do the brute force method and then just show you that it could have been done a lot simpler by just taking the difference between the domain below the upper plane and the domain below the lower plane. So here's a region. I mean, I'm just looking down along the z-axis. This yellow portion would be the portion which is the lower inclined plane. And at this point, this region here basically is where we're dealing with the z equals 0 plane. All right, so we know there's a discontinuity here, which means we'd have to look at an integral for this region plus an integral from this region. However, here we have a problem too, because if you look at just this region here, y is along this direction, x is along this direction, you do not have a smooth contour on the lower bound. So the upper bound, like if you look at an inner integral in terms of y as a function of x, would be this one. But the lower bound would be along here, and then there was this change in direction. So this is a discontinuous boundary. So that's also not allowed. However, if we break it at this point, then if we integrate over this region, and this region, and this region, that basically represents the total region. So that's what we'd have to do if we go the brute force method. This picture you can find at this link if you wish. And so what I've done basically is set up the integral for this region, which is the part in yellow, for this region, this is in red, and this in gray. And so for the yellow one, this yellow one would be from the upper plane to the lower plane. So there it is, upper, lower. And the bounds in the region, which would be the bounds with respect to y and x, would be this line and this line. So y is 2 minus x, and y equals 0. So that's this one and that one. And then x will range from 0 to 2, which is this one. So this one takes care of this region. For the red, this is now the upper plane. And so we're basically going from the lower plane to the upper plane, because in this section here, with reference to the z equals 0 plane. And so you can see z equals 0, 4 minus x minus y. If you look at the bounds on the y, it's this line and this line. Well, that's 4 minus x for this one and 2 minus x for this one. And we're going from 0 to 2 again, more or less this same distance. Finally, the gray region is again from 4 minus x minus y to the z equals 0 plane. But in this case, the lower limit for y is 0. The upper limit is 4 minus x. And we're going now from 2 to 4, which is what we've shown here. So you can add these all up. In fact, you can, through a number of tricks, you can show that this can be reduced to an integral that looks like this. This integral minus this integral, and you'll find that the result is 20 when you make the substitutions. But if you look at this carefully, what is this? This is actually the volume below the upper plane. And what is this one? This is actually the volume below the lower plane. That, in both cases, in the first octave. Well, I could have done that by inspection. I could have written these out by inspection. I just wanted to show here, and in fact, if you do the brute force method, we end up with finally the same result after a little bit of manipulation. Anyway, so that's an example of a problem that was solved, and it turns out that the right-hand side was clearly the easier approach to take in terms of solving the divergence theorem. All right, so now let's look at question 39 from chapter 17.8. And so this is Gauss's law, which is also called the divergence theorem for electric fields. And the electric field to a point charge q is E equals q divided by 4 pi epsilon naught, r divided by the magnitude of r cubed, r being a vector, and that vector has components x, y, z, and the epsilon is a constant. So the 4 questions are there. You can actually read them out. I'm not going to read them out. And just want to make a note here, because this last part, D, makes reference to del squared phi equals minus q epsilon naught. This is basically the Laplacian operating on a scalar function. And we actually looked at this in lecture 21b. And so this was the expression that we had for scalar Laplacian. If you have a divergence of a grad phi, the divergence is an operator. It has this form. This is like a dot product. So you have a dot product. And grad phi, this is the gradient applied to the scalar function. And so when you compute this, what you're doing is you have this one operate on this, plus this operate on this, plus this operate on that. When you expand it out, this just becomes the sum of second order derivatives in x, y, and z applied to the scalar function phi. And the short form for something written out in this form is just del squared phi. So this is basically the Laplacian of the scalar function phi. All right, so let's look at the answer to the first question. That is, show that the flux of the field across a sphere of radius A, center of the origin, is Q over epsilon naught. Okay, so we basically have to determine what the surface looks like. Now, you could solve this basically as a problem in spherical coordinates, and I'm going to solve it in Cartesian coordinates. It really doesn't matter. However, because it's in Cartesian, we basically have to look at the surface as two surfaces glued together, because the surface in explicit form, if we choose to go in explicit form, will involve a positive square root sign for the upper hemisphere and a negative square root sign for the lower hemisphere. And so here, for instance, is the upper hemisphere will be positive and the lower hemisphere will be minus. We want to compute the surface area vector for both upper and lower hemisphere. And so in explicit form, this would be minus z partial x minus z partial y and 1. And that's pointing in the positive direction, which would be actually the upper hemisphere. If it's the lower hemisphere, this would be z partial x partial y. Notice I've multiplied this by minus 1. And now this one basically is pointing downwards, which would be the case for the lower hemisphere. And so this is basically the differential surface area vector now for the upper hemisphere. That's when z is greater than or equal to 0. And this is for the one that's lower hemisphere, which is when z is less than or equal to 0. All right, so now basically we just take our expression for the field. We have the position vector, which is r, and r would be basically x, y, and z. Well, there's x, there's y, and z is the positive square root. All right, and our magnitude of r cubed. Well, magnitude of r cubed, basically, you would have to take this and take its magnitude, right? You'll end up with the square root of something, and then you take the third power. If you do that, and this is something you can do yourself, you end up basically with a cubed. All right, so this is the expression for the electric field for the upper. And then for the lower, if you go through the same procedure, in this case, you find you get the same answer. Okay, so this is purely mechanics. Just work through the mechanics, convince yourself that you get this result. Okay, so that means that E dot n ds, okay, E in this case, one is a positive, one is a minus, but the ds basically involves a positive here and a negative here. If you take the dot product for both of them, in other words, do this computation, right? So you're applying this one to this one and this one to this one, you'll end up more or less with exactly the same result. So the flux contribution for the upper hemisphere and lower hemisphere are identical, the same. And so what we do basically, we just now basically do the actual computation, and you just integrate the flux, which is E dot ds over the surface. And the region, of course, would be two semicircles, an upper bound and a lower bound, between radius in the x direction minus a and positive a. Now, if you do this computation here, you'll end up basically with simplification if we make use of polar coordinate transformation. Polar coordinate transformation means that x is r cos theta, y equals r sine theta. So this just becomes a squared minus r squared here. The dy dx gets replaced by r dr d theta, which is what you see here. And the region basically is of a region of a circle of radius a, which is equivalent to integrating from 0 to a for dr and from 0 to 2 pi for d theta. So if you do this calculation for one of the hemispheres, you get q over 2 epsilon naught. But since the integrals for both are identical and you're interested over the full closed surface, then you just have to take this result and multiply by 2. And so the closed surface integral of E dot n ds, which represents the total flux from that closed surface, is just q over epsilon naught. So more or less, we just proved the result above. Okay, part B. Suppose there is distribution of charge within region D. Let q, x, y, z be the charge density, units being charge per unit volume. Interpret the statement that the closed surface integral E dot ns ds is 1 over epsilon naught, integrating q, x, y, z dv over a volume, which is enclosed by the surface, with a factor 1 over epsilon naught in front. All right, so the solution is just an application of the divergence theorem. It states that if you sum the flux across the closed surface that bounds the domain D, then it's equivalent to determining the total charge contained within the domain D, multiplied by some constant that makes the units on both sides equivalent. In fact, if we moved epsilon to the left side and defined a new vector field D as D equals epsilon E, we normally call that the displacement field, not the electric field, then the closed surface integral of D dot n ds over a closed surface would be equal to the triple integral Q xyz dv, which is basically computing the total charge enclosed within the domain, and that domain basically has a bounding surface S. All right, so now we have a direct link between D and the total charge enclosed. All right, that would be a one-to-one relationship. Okay, so part C was assuming E satisfies the conditions of the divergence theorem on D, conclude from part B that the divergence of E is equal to Q over epsilon naught. And so the solution for this is just to apply the divergence theorem directly. So we know that E dot n ds is equivalent to saying divergence of E dv, where this domain basically is enclosed by this surface S. And we know that this equals this, so these two are equivalent to each other. But notice that they share basically a triple integral which is identical. This is over the same domain, integrate over volume. And so we can bring this over to the other side and write this out in this form. Now, for this to be 0, for all possible domains, because it's a very generic expression at this point, we're not specifying what the shape of the domain is. The only way that this can be 0 for all possible domains is if the integrand is equal to 0. And if the integrand is equal to 0, then that implies that divergence E equals Q over epsilon naught. Let's now consider question 39, part D, from chapter 17.8. The electric field can be expressed in the following form: E equals minus grad phi, where phi is a scalar function. Okay, that's basically what we'd like to basically determine. And so from part C, we then have to conclude that del squared phi equals minus Q epsilon naught. All right, so the solution basically starts by using Helmholtz theorem, and you can find this in lecture 21b. We know that any field can be constructed from a field which is irrotational and source-free. Okay, so if it's source-free, basically, then it's this term. If it's irrotational, it's this term. All right, so if we take the divergence of the electric field, all right, if we take the divergence electric, that means we take the divergence of these two here. And this is linear, so you can take divergence of this expression plus the divergence of this expression. If we take the divergence, that's minus divergence of the grad phi plus divergence of the curl of the vector potential A. But we also know from lecture 21b that the divergence of the curl of a vector potential is equal to 0. Okay, so if it's basically source-free, and this would be source-free, then the divergence basically equals to 0, which means that we're left with just minus del squared phi. And again, we know that this is equivalent to minus del squared phi. But divergence of E equals Q over epsilon naught. Therefore, minus del squared phi equals Q over epsilon naught. If you multiply through by -1 on both sides, then you end up with this expression here. So that would basically essentially prove part D. All right, let's look at another problem. This is question 47 in chapter 17.8. Consider the potential function phi xyz. G is function of rho, where G is any twice differentiable function, and rho is the square root of x squared plus y squared plus z squared. So this is more or less just a radius. Therefore, G depends only on the distance from the origin. So 4 parts here, and we're going to solve each in turn. You can just read through them because we're going to be basically repeating it anyways. All right, so for part B is to show that the gradient vector field associated with phi is F equals grad phi equals G prime rho R over rho prime. Okay, so R is this vector, and rho would be just the magnitude of this vector, which would be the square root of x squared plus y squared plus z squared. So the solution would be gradient of phi, which means we're going to be taking the gradient of G with respect to rho. And the gradient of G with respect to rho, if we write this out, would be just dg rho dx, dg rho dy, and g rho dz. Okay, so next basically is to realize that rho is a function of x, right? Y and z. And so we basically have to apply basically the chain rule. Since we're interested in x, that becomes g rho d rho to x for the x component, dg rho dy to d rho dy for the y component, and dg rho d rho dz for the z component. So that means we have two terms multiplying each other. If you look at these two multiplied together, you'll end up basically with a factor of g prime rho x over the magnitude of r. And I've shown down below basically how that's achieved. So for instance, the d rho by dx term here, that means you're taking derivative of this with respect to x. This is equivalent to x over the square root of x squared plus y squared plus z squared. But this is just the magnitude of r. So this is basically a short, sort of a condensed form of d rho dx. And you can perform a similar calculation to compute d rho dy and d rho dz. You'll just have this now being a y over magnitude of r and a z over magnitude of r. All right, so if you look at this now, you've got x, y, z over common r, but that basically can be written as r. Magnitude of r is rho, so rho can come outside, and the x, y, z remaining is just the vector r. And so this is the expression that you get for part A. All right, part B. Now, let S be the sphere of radius A, centered at the origin, and let D be the region enclosed by S. Show that the flux of F across S is the closed surface integral F dot NDS, which is equal to 4 pi A squared G prime A, G prime being a derivative. Solution is to use basically spherical coordinates. Let X equals A sine phi cos theta, Y equals sine phi sine theta, and Z equals A cos phi. And we're interested in basically the full sphere, so that means phi extends from 0 to pi, and theta from 0 to 2 pi. Again, r is x, y, z, that's the vector, it's a position vector, and rho is the magnitude of r. All right, so we need to basically compute t phi and t theta. We need to basically determine what NDS is. And so I've done this here. And for t theta, I end up with this term here. And then take the cross product of the two, d phi, d theta, which will be NDS. That's the differential area vector, which is normal to the surface. And if you look at this expression here, this basically just becomes a squared sine phi d theta, and it's pointing in the rho hat direction. So basically in a radial direction. All right, so this is more or less the radial direction. And so now we have to compute the vector field F. And if you do the computation of F, again, this is the x component, this is the y component, this is z component. We end up with g prime of rho, r vector divided by rho, rho being the magnitude square root of x squared plus y squared plus z squared, right? But this basically here is a unit vector. This is the actual radial vector, the unit vector, so that's why it's shown as rho hat. All right, so now we can actually do the computation of the flux integral. This is the flux over the full closed surface. We have F. We got this basically by substituting at the surface, right, which is at A. And we have 0 and 0. Okay, so this would be basically the two terms that we have. We have the component due to the surface area vector, which comes from here. Notice this is the r hat. This is going to be the phi hat vector. This is the theta hat vector. Here, same thing. There's only an r hat component. There's no phi hat component, no theta hat component. And there's the phi and theta basically, which is basically the surface over which you're integrating. And the norm to that surface, d phi, d theta, would be in the rho hat or r hat direction. Okay, so if we now take the dot product of this, the only term that survives is the dot product between this one and this one, which is a squared g prime a sine phi d theta. If you now integrate over the region, you end up with 4 pi a squared g prime a. And so that more or less proves is what we set out to do in at the very beginning. Okay, part C, show that the divergence of vector field, this divergence grad phi, is this expression here. Okay, so basically we just start with F is grad phi, is g prime rho r over rho. and expand this out in terms of the actual vector, x, y, z. If we now take the divergence of this expression, that means we're taking the divergence of all of this for the x component, all of this for the y component, all of this z component, and that means partial x of this, partial y of this, and partial z of this. All right, so now here again we have an issue in terms of the chain rule. This rho is a function of x, this is a function of x, and so we're going to have to break this up basically into, for each one of these, d by dx, you're going to have two terms. One having to deal with derivative of this term with respect to x, and one with respect to x for this term. And then chain rule, because rho is a function of x. So you'll notice here, for instance, we have, for the first term, that is partial x with respect to g prime rho, first with respect to rho, then with respect to x, times x of p, and then we have to take derivative of this term, keeping this one constant, so g prime of rho, and then d of x over rho dx. Similarly for this term, which is these two terms here, and similarly for this term, which is these two terms here. I claim then when you do all of this work, you end up with a second derivative of the g with respect to rho plus 2g prime rho divided by rho. All right, and so I've just shown here some details. We've used the chain rule to expand each term of the expression here. dx over rho dx is just d of this expression, dx. And if you go and do this, you'll end up with y squared plus z squared over the 3/2 power of x squared plus y squared plus z squared. And d rho by dx equals x over rho, right? You can write out similar expressions for dy and dx. Having done that, you have to add everything together, and there'll be a lot of cancellations taking place, and finally, you'll end up with this expression that you see here. All right, so the next is to look at part D of question 47. And here we're going to use part C to show that the flux across S, as given in part B, is also obtained by the volume integral. That's integrating the divergence of F over the domain, which is enclosed by the surface S. And there's a hint given here, that is to use spherical coordinates and integrate by parts. At least that is one possible way of doing it. But in fact, I'm showing you here that there's another option, and that is to recognize that the part in green can be actually simplified. So by all means, use integration by parts on the full expression, and we'll mention that as we walk through the solution. So the solution of the divergence of F, if you compute the divergence of F, this is 2 times derivative of g with respect to rho divided by rho plus the second derivative of g with respect to rho. All right, so that's basically just taking the derivative. Okay, so we're going to take the divergence of f, we're going to substitute it into the triple integral, and because it's spherical coordinates, that means that dv, that's the differential volume, is rho squared sine psi d rho d phi d theta. And because we're dealing with a sphere, that means the bounds on rho are going to be 0 to a. The bounds on phi will be from 0 to pi, and the bounds on theta are from 0 to 2 pi. So if we multiply through by rho squared here, we end up with this expression, and it's this expression here I'm basically suggesting can also be written as shown here. So if I took the derivative with respect to rho of this, and first take derivative with respect to rho squared, which is 2 rho g prime, and then rho squared comes out, and the derivative of this with respect with rho will just be g double prime. So that's the second derivative with respect to rho. So this can be replaced by that. And so this is what I've done here. I just introduced this expression here. And this will be just derivative of something with respect to rho, which means it's just rho squared g prime rho, a value between the upper bound a and 0. And then that just becomes a squared g prime a because we're evaluating at a. Upper bound and 0 lower bound. So the lower bound basically gives you a 0 contribution, and that means we're now just integrating with respect to phi and theta. And if we go through this process, we end up with 4 pi a squared g prime a. And this is consistent with the result that we got when we did the closed surface integral. So this concludes lecture 23b. Thank you for listening.